You see, we are moving relative to our universe, and then our universe destroyed, so now parallel universes, our multiverse, started to move parallel to us because we were out of alignment, and that just destroyed everything.
In a world where science fiction meets reality, a young prodigy, the world's smartest kid, has just dropped a bombshell that could change the course of human history. Right here at the cutting-edge facility of CERN, where mysteries of the universe are unlocked, a portal to another dimension has been unveiled. And the one who unraveled this astounding discovery? None other than a child genius, a modern-day Einstein, who's rewriting the rules of reality. But can we trust the claims of this prodigious youngster? And could this be the revelation of a lifetime? The world as we know it might never be the same again. So join us on this mind-bending journey as we dive deep into the realms of science and the unknown to uncover how the world's smartest kid has just revealed that CERN might have just opened the portal to another dimension. Throughout the years, the realm of science has witnessed its fair share of prodigious young minds, yet none have shone as brightly as Max Laughlin. This child prodigy is acclaimed as the world's smartest kid genius. Max's ingenious theories, particularly his insights into the Large Hadron Collider, have sent ripples of apprehension through the global scientific community. Initially, Max dazzled the world with his theories that unraveled the intricate workings of our world and how humanity adapts to the ever-evolving phenomena in our vast universe. However, his recent revelations transcend mere information. They sound alarms. The young physicist meticulously dissected his claims through captivating videos, offering comprehensive explanations that left scientists worldwide intrigued. Not only is Max an adept theorist, but he is also a prodigious inventor. Surprisingly, at the tender age of 13, he conceived a groundbreaking free energy device. With unwavering enthusiasm, Max demonstrated how this device could revolutionize the way people live across the globe. His invention held the promise of restructuring human existence itself. Since then, Max has gained widespread recognition for his ingenious perspectives on the captivating phenomena unfolding within our universe. Interestingly, the subjects Max delves into revolve around the very world we inhabit and the intriguing concept of parallel universes. Some of his most captivating theories revolve around our world, the experiments conducted at CERN, and the potential risks they pose to the very fabric of our universe. These experiments are carried out using the awe-inspiring Large Hadron Collider, a colossal machine designed to disassemble subatomic particles in an attempt to recreate the conditions of the Big Bang. Max's theories suggest that these experiments, while awe-inspiring, might have inadvertently jeopardized our universe, potentially causing a shift into a parallel universe. What's truly fascinating about Max's perspective is that he argues that our universe is just one thread in the vast tapestry of the multiverse, and there exists an infinite number of parallel universes alongside an infinite number of realities. In a sense, Max believes that we were once on a single linear timeline. However, during one of these experiments, an anomaly occurred, leading to an infinite series of shifts into alternate universes. It's as if we've embarked on an endless journey through the corridors of existence, continually leaping from one parallel universe to another. In our current reality, we find ourselves immersed in the idea of infinite universes. It's a concept that challenges the boundaries of our understanding. However, in the blink of an eye, our existence can be altered. The catalyst for this shift could very well be the remarkable minds at CERN, who upon detecting an anomaly in the space-time continuum embarked on a mission to manipulate pivotal moments in history. The profound notion underpinning their actions is that reality may not be as fixed as we perceive it to be. It's this belief that fuels the claims surrounding the European Organization for Nuclear Research's experiments aimed at opening portals between universes. Max Laughlin, a young visionary, reinforces this idea. He contends that these portal-opening experiments at CERN provide compelling evidence for the existence of neighboring universes, harmonizing with his theory of the Mandela effect. To understand this theory better, we must turn our attention to the colossal marvel known as the Large Hadron Collider. Nestled beneath the Earth's surface in a sprawling 17-mile tunnel straddling the borders of France and Switzerland, the Large Hadron Collider is the world's most potent particle accelerator. Inside this circular tunnel, scientists orchestrate the collision of two particle beams, meticulously scrutinizing the atoms and molecules that emerge from this cataclysmic encounter. The results offer a profound glimpse into the intricate dance of physics. In Max Laughlin's perspective, this awe-inspiring machine might have inadvertently led to our universe's displacement into an adjacent one. This seismic shift, according to Max, can be traced back to the Large Hadron Collider. The machine's reputation as a harbinger of change stretches back to the days of Bill Clinton's administration, fostering an air of mystery and intrigue that has captured the imagination of many. During the inception of the Large Hadron Collider, apprehensions ran high among the scientific community. Many feared that this colossal machine could potentially generate a black hole, spelling doom for our planet. This concern reached the zenith when Francesco Calogero, a distinguished nuclear physicist from the University of Rome and a co-recipient of the 1995 Nobel Peace Prize, penned an essay in 2000 titled "The Michael Tree Experiment: A Threat to Planet Earth." Calogero's essay ignited a protracted debate that raged for years, revolving around the pivotal question of whether the Large Hadron Collider was a harbinger of planetary destruction or a crucible of scientific discovery. The essay's reverberations extended far and wide, even making their way to John Oliver's segment on The Daily Show in 2009. In an episode featuring a science teacher, the Dyer claimed that the experiment held a 1 in 2 chance of birthing a cataclysmic black hole was aired. However, to quell these fears, John Oliver engaged with scientists from CERN actively involved in the Large Hadron Collider project. These experts systematically debunked the ominous predictions, reassuring the public that the Large Hadron Collider was a tool for profound scientific exploration, not a doomsday machine. Amidst this backdrop of scientific intrigue, the concept of the Mandela effect enters the stage. Max Laughlin, a brilliant mind of our time, affirms the reality of this phenomenon. The Mandela effect occurs when a substantial number of people collectively remember an event that, in fact, never transpired. This concept resonates with Max's theories as it challenges the conventional notions of reality and memory. The term Mandela effect was first coined in 2009 by Fiona Broome, who created a website to chronicle her experiences with this peculiar phenomenon. Broome's journey began during a conference where she engaged with others about her vivid recollection of Nelson Mandela's demise in the 1980s. It's noteworthy that Mandela did not pass away in prison during that decade. He left us in 2013. Fiona Broome's journey into the enigmatic world of the Mandela effect began as she conversed with others about her vivid memories of Nelson Mandela's supposed death in the 1980s. What astounded her was the realization that she was far from alone in her recollections. A surprising number of people also held distinct recollections of news coverage, including a widow's speech commemorating Mandela's demise, a stark contrast to the historical truth. This collective misremembering, now known as the Mandela effect, gave credence to Max Laughlin's intriguing theory. Our reality might be an alternate expansion of the universe. The name Mandela effect encapsulates this phenomenon, but it extends beyond the Mandela narrative. Other instances of false group memory include Mickey Mouse with or without suspenders and the iconic mirror mirror on the wall line from Snow White and the Seven Dwarfs. These instances paint a picture of how collective memory can diverge from factual events, further bolstering Max's theories of an ever-shifting reality. While the Mandela effect weaves a curious fabric of memory, scientists at CERN focus on another complex nature of the universe itself. The Large Hadron Collider serves as their portal to test theoretical predictions in particle physics, particularly those associated with the Standard Model, a comprehensive framework explaining much of the subatomic world. Despite the remarkable success of the Large Hadron Collider, including its groundbreaking runs from 2010 to 2013 and 2015 to 2018, the universe continues to hoard its mysteries. One such riddle is dark matter, which makes up the majority of matter in the cosmos and is typically invisible to our senses. Astronomers infer its existence from the gravitational pull it exerts, binding galaxies and galaxy clusters together. Dark matter remains a compelling cosmic puzzle. We understand its role as an invisible cosmic framework, yet its true nature eludes us. The Large Hadron Collider was conceived and constructed to unravel this enigma, seeking answers that could reshape our understanding of the universe. In 2010, a wave of anticipation swept through the scientific community as the Large Hadron Collider roared to life. Physicists around the world harbored high hopes that this colossal machine would unlock the secrets of the universe. They yearned for more than just the Higgs boson discovery, which was a monumental milestone in our understanding of particle physics. They believed the collider held the key to unraveling the mystery of dark matter, a cosmic ingredient that shrouds the universe in mystery. However, beyond the Higgs boson revelation, the collider's early runs yielded no further breakthroughs. The absence of discoveries left scientists with a lingering sense of anticipation and a thirst for the answers that remained tantalizingly out of reach. After the second run in 2018, the Large Hadron Collider was temporarily shuttered for crucial improvements and maintenance. The collider remained silent, undergoing meticulous upgrades and refurbishments for 3 years. It came back to life on April 22, 2022, marking a momentous occasion in the world of particle physics. The collider's third run, which commenced on July 5th, fell on the heels of the 10th anniversary of the Higgs boson discovery, adding a touch of historical significance to the occasion. When you stumble upon a headline about a new and exotic subatomic particle, there's a substantial likelihood that the discovery unfolded within the confines of the European Organization for Nuclear Research, known as CERN. A striking example of this occurred in January 2022, when CERN scientists unveiled their breakthrough, the discovery of the inscrutable X-particles. These X-particles, aptly named for their enigmatic and unknown structures, were unearthed amidst a vast sea of trillions of other particles within the quark-gluon plasma generated by the Large Hadron Collider. These elusive entities trace their origins back to the universe's infancy, mere millions of a second after the Big Bang. At that time, the cosmos was a seething trillion-degree soup teeming with quarks and gluons, elementary particles in their most primal form. Before these particles could settle and merge into the more familiar protons and neutrons that constitute matter today, a fleeting moment occurred. A tiny fraction of quarks and gluons combined, forming the short-lived X-particles. The precise mechanism behind the creation of X-particles remains a puzzle. However, unlocking this mystery holds the potential to illuminate the types of particles that grace the Earth during the universe's earliest moments, revealing the deep secrets of our cosmic history. Intriguingly, researchers at the CERN's facility embarked on the task of reproducing the elusive X-particles. They accomplished this feat by hurtling positively charged lead atoms toward each other at remarkable speeds. This collision process caused them to shatter and generate a fleeting burst of particles, similar to the primordial plasma that pervaded the universe during its earliest moments. Countless particles emerged, including the elusive X-particles. However, the real challenge lay in sifting through a staggering 13 billion head-on ion collisions to identify these rare X-particles. The task was similar to finding a needle in a cosmic haystack. The journey of the LHC doesn't end here. Intriguingly, on April 2022, the Large Hadron Collider roared back to life with a fresh burst of energy, reaching the maximum beam energy of 6.8 TeV. This revival marked the beginning of a new chapter as the LHC embarked on its third run, scheduled to continue until 2026. The world of particle physics buzzed with excitement as scientists anticipated further discoveries and breakthroughs. However, during this third run, another unexpected and baffling phenomenon took place. On July 7th, scientists at the LHC were left utterly perplexed when a crack appeared in Earth's magnetic field. This was no fleeting occurrence, as such phenomena often are. It endured for a remarkable 14 hours. This unusual breach allowed intense solar winds to stream through the opening, giving rise to colossal geomagnetic storms that painted the skies with mesmerizing auroras. The enchanting display of auroras captured the imaginations of science fiction enthusiasts, some even whimsically suggesting that it might be a gateway for the monstrous villain Vecna from Stranger Things to emerge into our world. Alas, that remained a dream for die-hard fans. So, how did this magnetic crack in Earth's protective shield come to be? The answer lies in a rare phenomenon called a co-rotating interaction region from the Sun, abbreviated as CIR. CIRs are large-scale plasma structures generated in the low and middle latitude regions of the heliosphere, that is, the vast expanse surrounding the Sun, when swift and sluggish streams of solar wind collide. Just as coronal mass ejections, CMEs, are flung from the Sun towards Earth, these CIRs can also bring shock waves and compressed magnetic fields, ushering in stormy space weather and magnificent auroras. The particular CIR responsible for this striking event impacted Earth's magnetic field in the early hours of July 7th, unleashing a long-lasting G1-class geomagnetic storm, according to the National Oceanic and Atmospheric Administration, NOAA. Now, the big question is, should we be concerned about such magnetic cracks? The experts assure us that this is a normal occurrence. Earth's magnetic field acts as a robust shield that defends us from solar storms and their potentially disruptive effects on technology. These magnetic cracks do occur from time to time, but are generally transient, quickly opening and closing. However, the recent event underscored the fact that such cracks can remain open for an extended period, revealing the occasional draftiness in our magnetic shield. As Harold Freya, lead author of a study on this phenomenon back in 2003, likened it saying, "Our magnetic shield is drafty, like a house with a window stuck open during a storm. This house deflects most of the storm, but the couch is ruined." In essence, the magnetic shield absorbs the brunt of space storms, but some energy manages to slip through its cracks. These minor energy incursions may occasionally disrupt satellites, radio communications, and power systems, but in this instance, there were no significant consequences in terms of radio blackouts or power outages. Meanwhile, the third run of the LHC is a pivotal phase in a grand scientific program. The first run, a groundbreaking triumph, unveiled the long-awaited Higgs boson, a particle fundamental to our understanding of mass in the universe. In the second run, the LHC delved even deeper, unearthing the major decay modes of the Higgs boson. These findings solidified the Higgs boson's role as the source of mass, especially for the relatively heavier elementary particles. As the third run unfolds, there's a sense of anticipation that it will double the existing LHC data set by its conclusion in late 2025. This will likely be succeeded by an extended period of preparations that may extend through 2029, gearing up for the LHC's next evolution. When the fully matured LHC comes back to life, it will astound us with collision rates 10 times higher than the present one, taking science to uncharted territories. The fourth run, estimated to last until 2042, promises an ultimate dataset nearly 10 times larger than what we could expect at the end of Run 3. At the heart of LHC physics lies the accumulation of massive data resulting from proton-proton collisions. Protons are the particles of choice due to their manageability and suitability for high-energy acceleration. Though not elementary particles themselves, protons are composite entities consisting of quarks bound together by gluons, the quanta of the strong nuclear force. To grasp the complex collisions at LHC, one can envision protons as bags of jelly beans, each housing quarks, gluons, antiquarks, and even heavier particles like the W and Z bosons, responsible for weak interactions and radioactive decay. When two protons collide, the most likely outcome is akin to two bags of jelly beans being torn apart, releasing particles that coalesce into protons, pions, and other familiar entities. However, occasionally, only two quarks or gluons collide head-on, condensing their energy into a minuscule space before dispersing it back into quarks, gluons, and even heavier particles. This intricate dance of particle interactions lies at the heart of the LHC's quest to decipher the fundamental building blocks of the universe, expanding our comprehension of the cosmos one collision at a time. Initially, the main aim of the LHC is to unearth new elementary particles, which could reveal previously unknown fundamental forces at play. Some of these proposed particles might be heavy and would break down into clusters of quarks and leptons, unleashing substantial energy. However, scientists don't anticipate discovering such particles in the upcoming Run 3. At best, they might gather intriguing statistical hints and suggestive event images with novel features. These would provide fodder for theoretical discussions. It's in the subsequent high-luminosity Large Hadron Collider runs, particularly Run 4, where these suggestions are poised to be confirmed. Currently, there's a significant opportunity to hunt for weakly coupled particles, particularly those predicted in dark matter models. These particles result from reactions driven by weak and electromagnetic forces, not strong interactions. Therefore, increasing the dataset becomes crucial. Dark matter particles interact too weakly to create visible signals in the LHC detectors. However, scientists can search for visible particles recoiling against invisible emissions in line with Newton's third law. Trigger enhancements in Run 3 are set to expand the scope for such subtle signals. The increased data rate will help uncover rarer events where recoiling particles become more visible. Moreover, CERN has laid out preliminary designs for a future circular collider poised to be the most potent particle smasher ever constructed. However, not everyone is on board with this endeavor. Sabine Hossenfelder, a theoretical physicist at the Frankfurt Institute of Advanced Studies in Germany, questions the investment's wisdom. She contends there's no concrete reason to expect new physics in the energy regime the new collider would reach. She suggests that allocating those hefty sums to other projects, such as a radio telescope on the far side of the moon or a gravitational wave detector in orbit, might offer more assured scientific returns. With the LHC still mid-stride in its third run, followed by preparations for a fourth, both of which promise substantial contributions to particle physics, the need for such an investment remains a subject of debate. Let us know your thoughts on this shocking revelation about the LHC, and thanks for watching another episode of Voyager. While you are still here, make sure to click the video on your screen for more quality content.